Lesson 5, Pulleys. This is a very specific application of the concepts underpinning connected particles. So let's start off with what a pulley actually is. It refers to a mechanical system which we can use to raise or lower an object. And here are some examples in this diagram here. You can see the man pulling on the rope here. The rope is attached to, passes over a pulley like so, and this results in him being able to raise this load here. So a pulley usually consists of a circular wheel with a grooved rim over which a rope passes. We can use the pulley to change the direction of a force. So again, look at the direction which the man is pulling and look at the direction in which the object ends up moving. It's much easier to pull down on a rope at an angle than it is for us to lift a heavy weight vertically. The use of a pulley allows these movements to be made more efficiently. Now, in mechanics, we usually model a pulley as being smooth and light. The rope passing over the pulley is modelled as being light and inextensible, so a light and inextensible string. Now, the quality of inextensibility here means that if a string is inextensible, this results in the tension being constant throughout the string. And in order to be able to carry out various calculations, we need to make this modelling assumption. So let's move straight into looking at an example. We have particles P and Q with masses of 5 kilograms and 2 kilograms respectively. They are attached to the ends of a light, inextensible string which passes over a smooth fixed pulley. The system is released from rest, and we need to find the acceleration of the system and the distance moved by P in the first 3 seconds of its motion. And we're given some further information here. We assume neither particle reaches the pulley. So the first thing that we're going to do is draw a force diagram. So here's my pulley, and there'll be a string that passes over the pulley, which is attached to 2 particles, let's say P and Q. Now let's include some forces in our diagram. P has a mass of 5 kilograms, so it has a weight acting downwards of 5g. Q has a mass of 2 kilograms, so weight of 2g acting downwards like so. And there will be a tension in the string here and a tension in the string here like that as well. Now, the tension is constant throughout the string because we have assumed it is inextensible, and that simplifies our calculations quite significantly. Now, because P is the heavier particle, when the system is released from rest, P will accelerate downwards with an acceleration, we'll call it A, and Q will accelerate upwards with the same acceleration. The acceleration is constant because the tension is constant throughout the string, which of course we know is inextensible. Now, let's have a look at our calculations. So we're going to start with particle P, and this is vertical motion. We need to make sure we choose a positive direction. Because P is moving downwards, I'm going to choose down as positive. Newton's second law of motion tells us resultant force equals mass multiplied by acceleration. So forces acting on P, we have 5g acting downwards in the positive direction, T acting upwards, which must be negative because it's in the opposite direction, equals the mass of the particle, which is 5, multiplied by its acceleration A. And we clearly have an equation with 2 unknowns, T and A. Call this equation 1. Now, particle Q, I'm going to choose up as the positive direction for its motion. Remember, we're treating the particles separately here, so actually I can choose a different direction to be positive if I want to, because it's a completely separate application of F equals ma. We're looking at the forces acting on Q. So this time we have in the positive direction upwards T. 2g is negative because it's downwards, and this equals m, which is 2 multiplied by the acceleration, which is still a. Now, we can clearly see we have a pair of simultaneous equations, and like we've done previously, we have a negative t and a positive t, so the simplest way of solving these is to add them together. So equation 1 plus equation 2 gives us 3g equals 7a, and therefore the acceleration is equal to 3g over 7 meters per second squared, and we can leave this in terms of g. Or we can calculate it, and it works out to be 4.2 meters per second squared. Now the last thing we need to do is to calculate the distance moved by p in the first 3 seconds of its motion. Now, we know the forces acting are constant, which means there must be a constant acceleration, which means that we can apply SUVAT, i.e. our equations of constant acceleration. So S is what we are actually looking for. U equals 0 because the system started from rest. V we don't know. A we've just calculated is 4.2 meters per second squared, and T is 3 seconds. So we're trying to find out the distance moved by P. So let's take out V because we're not interested in that. That leaves us with S, U, A and T, which means we can use the equation S equals UT plus a half AT squared, which is a half multiplied by 4.2 multiplied by 9, which gives us a final value of 18.9 meters to 3 significant figures. Notice we weren't in this question actually asked to calculate the tension in the string, but we could have used either simultaneous equation to go back and calculate the tension if needed once we had the acceleration. Let's look at a slightly different example. We have two particles, P and Q, of masses 6 kilograms and 3 kilograms, connected by a light inextensible string. P rests on a rough horizontal table and the string passes over a smooth pulley fixed at the edge of the table with Q hanging vertically. The system is released from rest and the magnitude of the frictional force experienced by P is 19.6 newtons. We've then got 3 calculations that we need to make. Let's draw a very clear force diagram for this situation. So here's my table, and on the end of the table there will be some kind of pulley. I'll shade the pulley in so we can all see it clearly. There's a string that passes over the pulley, and the string is attached to two particles, P and Q, like so. Now, let's put in some forces. Both the particles have a weight. P has a weight of 6g, Q has a weight of 3g. There will be a normal reaction force pushing up on P, the table pushing up on P here, which we'll just call R. And there will be tension in the string. There's a tension force that effectively keeps Q held upwards like that, and a tension force like that. The string is inextensible, which means that the tension is constant throughout the string. It's the same tension force acting on both P and Q. Now, there is a frictional force experienced by P because remember the table was rough. So that is going to be in this direction and it's 19.6 newtons. Let's just quickly think about why the friction would be acting in this direction. Now, the system is currently being held at rest and it's then going to be released from rest. As soon as it is released from rest, Q will start accelerating downwards like that. This will cause P to accelerate to the right like this. Remember, friction is a force that opposes both the direction of motion or the intended direction of motion. Particle P is attempting to be dragged towards the right, or Q is attempting to pull P to the right, which means the friction will act in the left, so in the opposite direction to try and oppose this motion. So, Our calculations are going to depend on us applying Newton's second law of motion, F equals ma, throughout. We're going to split the motion up and look at the forces acting on Q and look at the forces acting on P. I'm going to start with Q. I'm going to choose down as the positive direction because that's the direction in which it's moving. Let's look at the resultant force. 3G downwards, T upwards, that's the resultant force, or the combination of the forces with 3G downwards and T upwards, one positive and one negative. That equals the mass of Q, which is 3, multiplied by its acceleration A, and there we have an equation. Now, the forces acting on P, I'm going to take the right as positive because that's the direction of motion. We have T in this direction, minus 19.6 in the opposite direction, which equals the mass 6 multiplied by the acceleration A. And we find ourselves in familiar territory, where if we add these equations together, we will eliminate the variable T. And this gives us 3G minus 19.6 equals 9A. This then allows us to calculate the value of the acceleration, which comes to 1.08 recurring, 1.09 metres per second to 3 significant figures. Now, let's calculate the tension. So we've completed part A, the acceleration. Let's look at part B, calculating the tension. We need to substitute back into either equation. I'm going to substitute back into equation 2, very simply. So my tension equals 19.6 plus 6A, which gives me a value of 26.13 recurring, 26.1 newtons to 3 SF. And part B is complete. Part C, find the force exerted on the pulley. So let's take a closer look at the pulley. Now here it is, shaded in black. There is a particle P, remember here, and a particle Q, remember here. And if you recall, there's a tension force like this and a tension force like this, and we've just calculated the magnitude of this tension force. Let's now look at the forces acting on the pulley. There's going to be a force which is equal and opposite to the horizontal tension force, like this, which acts on the pulley. And there's going to be a vertical one as well, which is acting in an opposite direction to the vertical T force. Remember Newton's third law of motion. For every action, there is an equal and opposite reaction. So the forces exerted on the pulley look like this, these two green forces. Now, if we want to actually work out the overall force exerted on the pulley, we need to think about the effect of these two individual forces. So we've got one force like this, which has a value of 26.13 recurring. And then if I add the other vector force as well, like that, so I'm simply taking these two horizontal green forces and thinking about how we add vectors together, we add them end to end, the overall resultant force will be the hypotenuse here in our triangle. Think back to the work that you've done on vectors. If you want to know the overall resultant of two vectors, you draw the vectors end to end and then join up the start with the end, and this vector gives you your overall force. Now, how do I calculate the magnitude of this? I need to use Pythagoras Theorem. So that, of course, is going to be 26.13 recurring squared plus 26.13 recurring squared, all square rooted, which gives me a value of 36.9581, etc. So that's 37.0 newtons to 3 significant figures. Let's have a look at another example. Two particles, P and Q, of masses 1 kilogram and 2 kilograms, are hanging vertically from the ends of a light, inextensible string passing over a smooth, fixed pulley. The system is released from rest, with both particles a distance of 1.5 metres above a floor. When the particles have been moving for 0.5 seconds, the string breaks. This is a crucial point. Find the further time that elapses before P hits the floor. There is a lot to do in this question. We need a very clear force diagram to start with. Here's the pulley. Shade it in. Let's have a string passing over the pulley, and I'll attach P and Q to the ends. It doesn't really matter which way they are placed, or as long as we've labelled them clearly and we know which is which. So they've got masses of 1 kilogram and 2 kilograms, so weights of 1g and 2g respectively. There'll be a tension force like this, which is vertical in both cases in the string. And we know that the particles are on a level which is 1.5 metres above the ground. And the particles are moving for 0.5 seconds when the string breaks. So let's think about what's going to happen here. The system is held in place. It's in equilibrium. Once the system is released from rest, Q is the heavier particle, so it will accelerate downwards like that. P will, of course, because it's attached to the other end of the string, accelerate upwards like this. They will have the same acceleration because it's an inextensible string. The tension is constant throughout the string. Now, they move like this for 0.5 seconds, Q moving downwards and P moving upwards. At that time, 0.5 seconds, the string breaks. That means they're no longer attached to each other, and ultimately both particles will hit the ground. And we have got to find the further time that elapses before P hits the floor. So we know that we can use simultaneous equations and Newton's second law of motion to generate these equations by resolving the forces on each particle separately, which allows us to calculate acceleration. Let's start with particle P. We'll choose up as the positive direction because that's the principal direction of its motion, certainly to start with. We have T acting upwards in the positive direction, G or 1g downwards, which equals the mass 1 multiplied by the acceleration a. And we have our first equation. Q will take down as being positive, so we have 2g downwards, T upwards, and this is equal to the mass of Q, which is 2 multiplied by its acceleration. Now, let's add these together, as we've seen consistently in a lot of these examples. This will allow us to eliminate one variable, in this case T, and find the acceleration. So we have G is equal to 3a, so A is equal to 1/3 of G. And I'm going to leave that in its exact form for the moment. So we know that the system will run for 0.5 seconds before the string breaks. So let's start splitting up the motion. You'll notice I haven't calculated the value of the tension because I'm not sure that I'm going to need it. This looks like it's going to develop into a suvat problem. So before the string breaks, we can calculate a number of pieces of information. So we can calculate the distance travelled. Q will travel a certain distance downwards and P will travel the exact same distance upwards. We can work this out. We don't know what it is. U is equal to 0 because the system was at rest. V we don't know, but we may want to work out V potentially. Acceleration is 1/3 of G, and the time we know is 0.5 seconds. So let's work out the distance first of all. So this means we're going to calculate S. So S equals ut plus a half at squared. allows us to calculate how far the system has moved in 0.5 seconds. So let's do this. We've got a half times 1/3 of g multiplied by 0.5 squared, which equals 0.4083 recurring meters. And I'm going to store that in a calculator memory. Just make sure you know which memory you've stored this in. Now, I'm also going to calculate v, the velocity with which P and Q, they'll have the same velocity, the velocity with which these particles are travelling when the string breaks. So v equals u plus at, so that's equal to 0 plus 1/3 of g multiplied by 0.5, which simply comes to a value of 1.63 recurring meters per second, which I'm going to store in another memory. I'll store this in memory B. Now, after the string breaks, P is not instantaneously going to start falling towards the ground. It will have some degree of what we call momentum because it had a velocity and it was moving upwards. It will carry on moving upwards until it hits zero velocity. So at the point at which the string breaks, P is travelling upwards with the velocity that we have just calculated, 1.63 recurring meters per second. It's travelling under gravity, so this is vertical motion under gravity. So its acceleration is the acceleration due to gravity, and it will be decelerating upwards towards a zero velocity, at which point it will start moving downwards again. So let's see if we can do some calculations. So the first thing we want to do is look at the upwards motion of P. Now, the acceleration will be 9.8 meters per second squared downwards because it's in the same direction as the weight. But just before the string broke, so at the point at which the string broke, this particle was travelling with a velocity that was vertically upwards, and this velocity was equal to 1.63 recurring meters per second. So let's apply some SUVAT information. S, we don't know, but we may want to work it out. U is equal to 1.63 because it's actually the velocity with which P has started this new section of its journey. V, the final velocity, is 0 because we're working out how long it takes the particle P to hit this 0 velocity. A is negative 9.8 meters per second squared because I am going to choose upwards as positive. And T, we don't know the value of. But we're going to work out how far it travels, and we're going to work out the time taken to travel this distance upwards to a point of 0 velocity. So first of all, let's have a think about the equations we could use. We can use v squared equals u squared plus 2as, which doesn't involve t, and this will allow us to work out the value of s. So 0 equals 1.63 squared plus 2 times negative 9.8 multiplied by s. Let's rearrange this to work out the value of s. And this comes to 0.1361 recurring meters. I'm not going to round it just for the moment, but I am going to save it in a calculator memory and write down which memory that is. So this is the distance travelled upwards by P after the string breaks due to its momentum. Now, how long does it take to complete this portion of its journey? V equals u plus at. So 0 equals 1.63 recurring plus negative 9.8 multiplied by t. We can work the value of t. And this is equal to 0.16 recurring seconds. So again, just to clarify, this is the time taken by P to travel upwards to 0 velocity, the highest point of its motion, after the string breaks. So now let's think about P's journey downwards from its highest point of motion. So at the very beginning, P was 1.5 metres above the ground. We then calculated that before the string broke, whilst P and Q were still connected, P travelled a distance of 0.4083 metres upwards. Now, after the string broke, we then calculated that P travelled a further distance upwards, which was equal to 0.1361 recurring metres. So that's after string breaks, as P reaches its maximum height. The last part of the motion is going to be P on its downwards journey. So P travelling all the way down to the ground like that. And we now know the total distance that P would travel. So we need to work out the further time that elapses. So if you recall, that's going to include the time taken for P to complete this journey and the time taken for P to complete this journey here as well. Now we already know the time taken for the green part of the journey, we calculated it previously. Let's now calculate the time taken for P to complete the yellow part of its journey. So I'll call this downwards. Let's apply suvat. P is in free fall. Its only force acting is weight, which means it's working under gravity. So weight is a constant force, which means the acceleration will be constant, and it's the acceleration due to gravity. So let's take down as positive because P is travelling downwards with an acceleration of 9.8 metres per second squared. So A equals 9.8. It starts off with 0 velocity, which is the velocity it reached at the top of its motion, so 0. We don't know what V is, and I don't think we actually need to work it out as well, so we'll remove that. T is what we actually want to find out, and S is going to equal these three distances added together, so 1.5 plus 0.4083 recurring. We're going to use full accuracy, plus 0.1361 recurring, which add together to make a total distance of 2.04 recurring metres, which I'm going to put in another memory. We'll put this in memory E. We can now calculate the key piece of information we need, which is the time taken to complete this downwards yellow journey. So let's use the fact that S equals ut plus a half at squared. So S, the total distance travelled, is 2.04 recurring. U is 0, so the first part of this cancels out. A half multiplied by 9.8 multiplied by t squared. So the time taken to complete the downwards journey works out to be 0.64593 ... So the last part of this calculation is to work out the time taken between the string breaking and P hitting the floor. So that's the time taken for the green portion of the journey, which is 0.16 recurring seconds, and we need to add on the time taken for the whole downwards portion of the journey, 0.64593, etc., and add these two times together. And this gives us a total time of 0.81260, etc., 0.813 seconds to 3 significant figures. Now let's look at example 4, where we have 2 pulleys. Let's read through all the information. We have a block of mass 5m kilograms. Notice that this m here is an algebraic m, it's an unknown. It's in equilibrium on a rough horizontal table, and it's connected by horizontal light inextensible strings over smooth pulleys to particles of mass m kilograms and 2m kilograms which hang freely. We now need to find the frictional force acting on the block and indicate its direction. So we can annotate this diagram with the forces acting. So I'm going to start with the weights of the objects in question. So we have the weight of this block, which is 5 mg, the weight of this particle, which is mg, and the weight of this particle, 2 mg. There will be a tension upwards like that, and that will be balanced by a tension across like that. There will be a different tension here, balanced by a tension here. There are 2 separate strings. This means that each separate string will have its own tension values. So we have to use T1 and T2 for this to be correct. The last force acting vertically is a normal reaction force of the table pushing up on the 5m block. Now, we need to draw on the frictional force as well between the block and the table. The system is actually in equilibrium, which means forces are balanced, but if it were released from rest, then the likely outcome would be this block would move downwards like that, as it's heavier than the other particle. This block would then consequently move across like that, and this one would move up like that. So friction always opposes the direction of motion, or the intended direction of motion, which suggests to me that the friction should be in this direction here. But it doesn't matter. If we're wrong, then the friction will work out to be negative, and we can clearly state that we should have put it in the other direction. So remember, the whole system is in equilibrium this time, so we're not using F equals ma. We're using the fact that equilibrium tells us that the resultant force is equal to 0. So for simplicity, I'm going to label the items. That's item A, this is item B, and this is item C, so you know which one I'm talking about. Item A, first of all, now the forces are balanced, so T1 has got to equal mg. Item B, I'm going to focus on the horizontal forces here because I know that the normal reaction is going to equal the weight, but that doesn't tell me anything particularly interesting for the moment. So horizontally, T2 has got to be balanced by T1 plus the frictional force. Just make that a curly F for clarity. And then the last object is object C. Again, we've got a pair of vertical forces, and T2 has got to equal 2mg. So we can now substitute in T1 and T2, which will give us a result for F. So T2 is the same as 2mg, which is equal to T1, which is mg, plus F. And if we rearrange this, F very simply works out to be mg, and it's come out as positive, so we clearly chose the correct direction. So towards the left. So we move on to another extensive question. 2 particles A and B connected by a light inextensible string. A resting on a smooth horizontal table, 1 metre from a fixed smooth pulley at the edge of the table. The string passes over the pulley and B hangs freely 0.75 metres above the floor. System is released from rest with the string taut, and then after 0.5 seconds the string breaks. Now we have 3 instructions here as to calculations we will need to complete. Find the distance the particles have moved when the string breaks, the velocity of the particles when the string breaks, the further time that elapses before A reaches the floor, given that the table is 0.9 metres high. So the first task, of course, is to draw a really clear diagram. So our table is going to look like this. And on the end of our table, we will have a pulley fixed on the end. Shade that in for clarity. Then the string passes over the pulley, like so, and is attached to the 2 particles. So particle A, which has a mass of 0.5 kilograms, so a weight of 0.5 g, and particle B, which has a weight of 0.7 g. Let's draw on the normal reaction force, the table pushing up on A. Now it's a smooth horizontal table, so that means there's no friction between A and the table. There is a tension force, like so, and an equivalent tension. So we know that A is 1 metre away from the pulley at the start of the motion, and we know that B is a measurement of 0.75 metres above the ground, and the system is released from rest. Okay, so the first thing that we are going to do is to look at the forces on A and then the forces on B separately. We're going to apply F equals ma. Once the system is released from rest, B will start to accelerate downwards like that, A will accelerate to the right like that. So we will make use of Newton's second law of motion, resultant force is mass times acceleration, starting with particle A, and we'll take going to the right as positive because that's the direction of its motion. So the only force we have acting horizontally is T, which is equal to the mass of A multiplied by its acceleration. Now, particle B, next of all, we'll take down as positive. We have 0.7 g downwards, T upwards, and this equals the mass 0.7 multiplied by the acceleration. And here we have our very familiar pair of equations. We'll call that equation 1 and equation 2. Again, as we've been seeing, we have a positive t and a negative t, so we can simply add the equations together, which gives us 0.7 g is equal to 1.2a, and from here we can calculate the acceleration. So the acceleration works out to be 5.716 recurring, and all I'm going to do is store that in a calculator memory because we're actually not asked to provide the value of the acceleration. We're asked to calculate the distance the particles have moved when the string breaks. So remember the modelling assumptions. The string is inextensible, which means the tension is constant throughout the string, which means the acceleration of the particles is constant and is the same for both particles. All of these ideas build on these initial modelling assumptions. And because we have constant acceleration, this tells us that we can use our equations of constant acceleration, the Suvat equations. So S is what we're actually trying to find. U we know is 0, the system starts from rest. V we don't know, and I don't think we're actually required to find it to begin with. A, the acceleration we've just calculated, 5.716 recurring. And T is equal to 0.5 seconds. So we can use s equals ut plus a half at squared to calculate the distance travelled. So that's a half multiplied by the acceleration multiplied by the time squared, and this gives us a value 0.714583 recurring, which we will round to 3 significant figures, but we will store the unrounded value in a calculator memory in case we need it. So this is the answer to part A. Now part B asks us to calculate the velocity of the particles when the string breaks. Of course, they'll both be travelling with the same velocity. So using the same SUVAT information, we can say that v equals u plus at. U is equal to 0, so we simply need to multiply our acceleration by the time, 0.5, which gives us a value of 2.8583 recurring, or 2.86 metres per second, 3 significant figures. And again, I'm going to store this value in my calculator. Now, in part C, we are investigating what happens after the string breaks. Now, when the string breaks, the piece of string that's still attached to A is slack. That means the tension is equal to 0. Now, if you recall, the table was smooth, so there are no further horizontal forces acting, which means that the acceleration is equal to 0, which means that A travels at a constant speed until it reaches the end of the table. We're then assuming it can bounce over the pulley and then down towards the ground here, and we need to find out the total time taken. So, before A reaches the pulley, we know it's travelled a distance of 0.71458 metres. Because A started off 1 metre away from the pulley, we can then work out this distance here, the distance left to travel before it reaches the pulley. So that's 1 take away 0.71458, which gives us a value of 0.28541. We won't round that value for the moment. Now remember, until A reaches the pulley, we've said it's travelling at a constant speed, so we can simply use speed equals distance over time, and its speed is the speed it was travelling at the point when the string broke. Now we know what that speed is equal to. It's equal to 2.8583 recurring. So the time taken to reach the pulley after the string breaks is equal to the distance travelled divided by the time taken, which is equal to 0.0998 ... Now we're not going to round this, we're simply going to store this in a calculator memory. Now let's think about what happens after A reaches the pulley. We're assuming it can simply skim over the top of the pulley, and A will then be travelling vertically downwards like this, under gravity, freely under gravity, as there are no other external forces acting. So we can say A accelerates downwards under gravity. Now, this is a constant force, which means the acceleration is constant. We have vertical motion under gravity. We can use our equations of constant acceleration, our SUVAT equations. Now, the distance travelled is the height of the table, so 0.9 metres. the velocity with which we start our downwards motion is 0. It is not the velocity 2.8583 recurring this velocity, because that was a horizontal velocity, and what we have here is a starting point of a vertical motion, so it starts off with 0 velocity. The final velocity we don't know. The acceleration is equal to 9.8. We haven't marked this on, but we should have. Downwards is positive. And the time taken is what we're actually trying to calculate. So excluding v, we don't need that information. So s equals ut plus a half at squared again. So 0.9 is equal to a half multiplied by 9.8 multiplied by t squared, and we can calculate the value of t, and it works out to be an exact value of 3/7. So to finish this off, the total time taken before A reaches the ground is 3/7 plus this value over here, 0.0998, and that comes to a final answer of 0.5284, etc. So 0.528 seconds to 3 significant figures. And so we reach our last example. Two particles, P and Q, masses 0.8 kilograms and 0.6 kilograms, connected by a light, inextensible string. P rests on a rough horizontal table at a distance of 1.7 metres away from a smooth fixed pulley at the edge of the table. The string passes over the pulley and Q hangs freely 0.5 metres above the floor. The system is released from rest, and the magnitude of the frictional force between P and the table is 0.2 g newtons. And we have 4 things that we need to calculate. The first 2 of which will be very, very quick to do once we've looked at our forces. So let's sketch the situation. We have a rough horizontal table, and here is the pulley at the end of the table, shaded in for clarity. Let's draw in the string, which passes over and here, and connects up to particle P and particle Q. We know what their weights are, 0.8 g for P and 0.6 g for Q. And we know that there'll be a reaction force here of the table pushing up on P, a normal reaction. Let's add in the tensions. P is being pulled towards the pulley like that, and a tension in the string here keeps Q held upwards like that to start off with. Now there are some measurements that we should add into our diagram, and we know that P is 1.7 metres pulley at the start of the journey, and we know that Q hangs freely 0.5 metres above the ground. These diagrams, these force diagrams, are not sketched to scale. You can see that 0.7 looks smaller than 0.5 here, but it doesn't matter. It's just knowing the values that's important. Now there's one last force that we need to add in place. There's a frictional force between P and the table. Now we know that Q is going to start accelerating downwards as soon as the system is released from rest. So P will start accelerating in this direction, which means that the frictional force will oppose this motion, and we'll put a curly F here for the frictional force between P and the table. So we've done this before. F equals ma will allow us to look at forces acting on the particles. I've written it in a vector format here. It doesn't really matter because we're only really looking at the particles separately. Let's have a look at the forces on Q first of all. I'll take down as positive. So what do we have? We have 0.6 g positive minus t, because that's upwards, equals the mass, which is 0.6 multiplied by the acceleration, and we straight away have our first equation. Let's do the same for particle P, but we'll take right as positive. That's the direction of motion once the system is released from rest. T is positive minus the friction, and that is equal to 0.8 A. And we're going to add these two equations together because, of course, as we've done previously, this will allow us to cancel out the plus and the minus t. So adding these together, we have 0.6g minus friction equals 1.4a. But of course, we know the friction is equal to 0.2g. So we can fill that in. This then allows us to calculate the acceleration, which works out very neatly to be an exact 2.8 meters per second. Substitute back into either equation. We'll substitute into equation 2 as it looks a little bit simpler. So t is equal to F plus 0.8 multiplied by the acceleration, which gives us a value of 4.2 newtons for the tension. So we've answered part A and we've answered part B simultaneously. So part C, we have to calculate the speed with which Q hits the floor. Here's a quick diagram that shows us the information that we have. We're not including all the forces on this for the moment because we're focusing on the kinematics of the situation. Q has to travel a distance of 0.5 meters from the ground. It has an acceleration which we've just calculated as 2.8 meters per second squared. Remember all our modelling assumptions. The string is inextensible, which means the tension is constant throughout the string, which means the acceleration is constant, which means that we can apply our equations of constant acceleration, or Suvat equations. Let's fill in the information that we have. The system starts off from rest. V is what we're actually trying to calculate, and we don't know what the time is. We may need that later on though. So this looks like a clear setup for v squared equals u squared plus 2as. Let's fill in the information that we have. We're choosing down as positive because all of the movement is downwards. So this then gives us 2 multiplied by 2.8 multiplied by 0.5, and from here we can simply work out the velocity, which comes to a value of 1.6733 ... I'm going to store that in a calculator memory and write down which one I've stored it in. So that is part 3, or part C, complete. Now, part D, we have to calculate the distance P moves after Q hits the floor. So after Q hits the floor, we now know that the string will become slack. So it's no longer taut. This tells us that the tension will be equal to 0. So the only horizontal force acting on P will be friction. And we have to reassess the situation. So let's see what we can now do. We know that P was originally 1.7 meters away from the edge of the table, but seeing as Q travelled 0.5 meters downwards, P must have travelled 0.5 meters along, meaning that there is a distance of 1.2 meters between P and the pulley at the edge of the table. So let's review what we already know. When Q hits the ground, remember, the string becomes slack, which means the tension is equal to 0, which means the only force acting on P horizontally is the frictional force. Now, the acceleration of P will change once Q hits the ground. Let's have a look at drawing a quick force diagram. We have the friction acting in this direction because remember it's opposing the motion, it's equal to 0.2g. P has a residual velocity which is taking it in this direction, we'll call going to the right positive. And we're going to work out this new acceleration once Q has hit the ground. So F equals ma, we've taken going to the right as positive, so the resultant force is essentially this frictional force, which is negative 0.2 g. That's equal to the mass of P, which is 0.8, multiplied by this new value of the acceleration, which comes to negative 2.45 meters per second squared. And that makes perfect sense. P was accelerating horizontally because of the pulley system, because of the tension generated in the string due to the weight of Q moving downwards, which pulled P along. Now that that string is slack, there is no tension pulling P along. It's got some residual velocity, but the friction is working against it to oppose the motion and to try and bring P to a stop. So that's why it is decelerating. So we need to know the distance moved by P. Now, the only horizontal force acting on P is the friction. It's a constant force, which means the acceleration is constant, which means we can apply our Suvat equations. So distance travelled is what we are actually looking for. Now, the velocity of P as its starting velocity is the velocity with which P was travelling at the moment when Q hit the floor. And we know that because it's the same speed with which Q hit the floor, and we've calculated it previously. It's this value, 1.6733. Now, we're assuming that P will either come to a rest before it reaches the pulley, or it will hit the pulley. We don't know. So let's find out how long it takes for P to come to rest, or how far P travels before it actually comes to rest. The acceleration is negative 2.45. We've just calculated that, and we don't know what the time is, and I think we're not going to use that variable. So v squared equals u squared plus 2as again. So 0 equals 1.673 ... squared. Using full calculator accuracy, remember, careful here because I know that s and 5 can look a little bit confusing. I've highlighted the s in green to avoid any confusion. So rearrange this equation and find out the value of s, the distance travelled. And this comes to a value of 0.57142, which rounds to 0.571 metres to 3 significant figures. So that is how far P moves after Q hits the floor, and we can see that this is less than 1.2 metres, so P is not going to hit the pulley.